And the crazy part is, that single recommendation engine at Netflix is responsible for something like 80% of their streamed content. 80%! Can you imagine the system design complexity behind that?
Wow, 80%. That's insane. So if that system hiccups, Netflix basically grinds to a halt. It's not just a bad user experience, it's a massive business risk.
Exactly. And that's why we need to talk about ML system design. It's not just about building a cool model in a Jupyter notebook. It's about taking that model and turning it into a reliable, scalable, and useful product. Think about Uber's surge pricing. Get the ML system wrong there, and you've got drivers quitting, riders complaining, and the whole marketplace collapsing.
Right. I think a lot of engineers, especially those newer to ML, focus primarily on model accuracy. They nail the algorithm, get impressive metrics in their test environment, and then the real world hits. Performance tanks, data drifts, and suddenly the whole thing is a mess. They didn't consider the full system.
Precisely. It's like building a race car engine but forgetting about the wheels, the chassis, and the steering wheel. You've got power, but you can't actually drive anywhere. So today, let's break down the full stack of ML system design, the things every ML engineer needs to know to build robust, production-ready systems.
Okay, I'm in. Where do we start? Data ingestion, right? That seems like the obvious first step.
Absolutely. Data ingestion is the foundation, but it's not just about dumping data into a database. It's about designing a pipeline that can handle the volume, velocity, and variety of data your ML system needs. Think about Google's search ranking algorithm. They're ingesting billions of signals every single day. Website content, user behavior, location data, you name it.
Okay, so scale is definitely a factor. But what about data quality? It's garbage in, garbage out, right?
100%. Data validation is crucial. You need to have systems in place to detect and handle missing data, outliers, and inconsistencies. Imagine building a fraud detection system for a bank. If your data is full of errors or biased samples, your model will be useless or worse, actively harmful.
So what kind of tools and techniques are we talking about here? Are we talking about custom scripts, or are there more robust frameworks available?
It depends on the scale and complexity. For smaller projects, you might get away with some custom Python scripts and some basic data validation libraries. But for larger, more complex systems, you'll want to look at tools like Apache Kafka for streaming data, Apache Spark for distributed processing, and frameworks like TensorFlow Data Validation, TFDV, for automated data analysis and anomaly detection. Think about how Cloudflare handles DDoS attacks. They need to ingest and analyze massive amounts of network traffic in real time to identify and block malicious requests. Their data ingestion pipeline is a marvel of engineering.
That makes sense. So we've got data ingestion and validation covered. What's next? Feature engineering, I assume?
You nailed it. Feature engineering is where you transform raw data into meaningful inputs for your ML model. It's both an art and a science. Think about predicting customer churn for a subscription service. You might start with basic data like age, location, and subscription tier. But then you might engineer more complex features, like average time spent on the platform per week, number of support tickets opened in the last month, or ratio of successful logins to failed logins.
So it's about finding the signals that are most predictive of the outcome you're trying to predict. But how do you know which features to create? Is it just trial and error?
There's definitely an element of experimentation involved, but it's not just random guessing. You need to have a deep understanding of the data and the problem you're trying to solve. Domain expertise is crucial here. And you can use techniques like feature selection and dimensionality reduction to identify the most important features and reduce the complexity of your model.
Okay, that makes sense. So data comes in, it's cleaned and validated, features are engineered, then we finally get to the model, training, evaluation, all that jazz.
Not so fast. There's one more crucial step before we get to the model, the feature store.
The what? I haven't heard of that.
This is where it gets interesting. The feature store is a centralized repository for storing and managing features. It's like a data warehouse specifically designed for ML features. The crazy part is, many teams skip this, and it leads to massive headaches down the road.
Okay, I'm intrigued. Why is it so important? What problems does it solve?
Think about it this way. You've got different teams working on different models, all using the same underlying data. Without a feature store, each team is going to end up re-implementing the same feature engineering logic over and over again. That's a huge waste of time and resources. And even worse, they might implement it slightly differently, leading to inconsistencies and errors.
Ah, so it's about consistency and reusability. It prevents everyone from reinventing the wheel, and it ensures that everyone is using the same version of the truth.
Exactly. And it also solves the training-serving skew problem.
Training serving skew? What's that?
That's when your model performs well during training but poorly in production. One of the main causes of training-serving skew is differences in the way features are calculated during training and serving. The feature store ensures that the same feature engineering logic is used in both environments, minimizing this risk. Think about how Stripe handles fraud detection. They need to calculate features in real time to assess the risk of each transaction. A feature store ensures that those features are consistent with the features used to train their fraud detection models.
Okay, that makes a lot of sense. I can see how a feature store could be a game changer, especially for larger organizations with multiple ML teams. So now can we talk about models?
Yes, now we can talk about models. Model training, evaluation, and selection are obviously crucial parts of the ML system design process. But I'm not going to spend too much time on that because most engineers are already familiar with the basics. We're talking algorithms, frameworks like TensorFlow and PyTorch, hyperparameter tuning, and all that good stuff. The key here is to remember that model performance is just one piece of the puzzle. You also need to consider factors like model size, latency, and interpretability.
Right. A super accurate model that takes 5 seconds to make a prediction is useless in many real-world applications.
Exactly. Think about self-driving cars. They need to make decisions in milliseconds, so you might need to sacrifice some accuracy for speed. Model deployment is where things get interesting again.
How so? I always thought deployment was just a matter of wrapping the model in an API and sticking it behind a load balancer.
Oh, if only it were so simple. Model deployment is a whole field in itself. You need to consider things like deployment environment, cloud, edge, or on-premise, deployment strategy, batch, online, shadow, and infrastructure requirements, CPU, GPU, memory. And you need to automate the entire process so you can deploy new models quickly and reliably.
So it's about more than just getting the model running. It's about building a scalable and resilient infrastructure that can handle the load.
Precisely. Think about how Meta deploys their ML models to billions of users around the world. They have a massive, highly distributed infrastructure that can handle incredible amounts of traffic. They use techniques like model quantization and distillation to reduce model size and latency. And they use canary deployments to gradually roll out new models and monitor their performance.
Okay, so we've got data ingestion, feature engineering, feature store, model training, and model deployment. Is that it? Are we done?
Not even close. The final and arguably most important piece of the puzzle is model monitoring.
Ah, yes. I was wondering when we'd get to that, because models don't just stay accurate forever, do they?
Nope. Data drifts, user behavior changes, and the world evolves. Your model that was performing perfectly yesterday might be completely useless tomorrow. You need to have systems in place to continuously monitor your model's performance and detect when it's starting to degrade.
So what kind of metrics are we talking about here? Are we just looking at accuracy and precision?
Those are important, but you also need to monitor things like data drift, concept drift, and prediction bias. Data drift is when the distribution of your input data changes over time. Concept drift is when the relationship between your input data and your target variable changes. And prediction bias is when your model consistently makes errors for certain groups of users. Think about Amazon's recommendation engine. They're constantly monitoring the performance of their models to ensure that they're still relevant and accurate. They use techniques like A/B testing and bandit algorithms to experiment with new models and optimize their recommendations.
Okay, so it's a continuous cycle. You monitor your model's performance, you detect problems, you retrain your model, and you redeploy it. And then you start all over again.
Exactly. That's the essence of ML system design. It's not a one-time project, it's an ongoing process.
So what's the biggest mistake you see engineers making when it comes to ML system design?
I think the biggest mistake is treating ML as an isolated component separate from the rest of the system. They focus on building a great model, but they don't think about how that model will integrate with the rest of the application. They don't think about data ingestion, feature engineering, deployment, or monitoring. They treat it like a black box.
And that's a recipe for disaster, right?
Absolutely. It's like trying to build a house without a foundation. The house might look great on the outside, but it's going to collapse eventually.
Okay, so what's the practical takeaway here? What should a software engineer do differently after listening to this? Give me 3 actionable things.
Okay, here are 3 things you can do today to improve your ML system design skills. 1. Think full stack. Don't just focus on the model. Consider the entire pipeline from data ingestion to monitoring. 2. Embrace automation. Automate as much as possible from data validation to model deployment. And 3. Monitor everything. Continuously monitor your model's performance and be prepared to retrain and redeploy it as needed. Think of it like tending a garden. You can't just plant the seeds and walk away. You need to water, weed, and prune regularly. That's great advice. I think those 3 points really encapsulate the key principles of ML system design. And remember, ML system design is not just about technology. It's also about people and process.